Shortly after Karatsuba and Hoffman proposed their way to speed up multiplication of numbers based on bit operations, Strassen came with a very similar in style algorithm of divide and conquer, but for matrix multiplication. And when we're talking about multiplying matrices, the atomic operations for us are not usually bit operations, but rather operations on elements of these matrices. So if these are matrices made of numbers, then multiplying or adding or subtracting, dividing numbers is what we supposed to be doable in 1 unit of time. And we count the number of these elementary operations in our algorithms. This is sometimes called the arithmetic complexity, the number of arithmetic operations that we need to perform to produce a result of some algebraic operation like matrix multiplication. So let's discuss Strassen's algorithm. In the algorithm of Strassen, we have two matrices of order n by n, and we could have written something like these matrices are made of real numbers, which would be denoted like this, where a Blackboard font R stands for the set of all reals. But we'll actually use this different type of R, where this R stands not for reals, but rather for a ring. A ring is a set with operations of addition and multiplication, which satisfies most of the properties we expect from addition and multiplication of real numbers. Like addition and multiplication both should be associative, addition should be commutative. For real numbers, multiplication is commutative as well, but not by default for rings. Multiplication should be distributive over addition. So in a lot of ways, rings behave the same as just numbers, but they are more general. So, for instance, matrices, with respect to adding them, multiplying them, they also form a ring. But for now, you can assume that these are actually matrices made out of real numbers or of integers. And we have a matrix C, which is the product of A and B. C is, of course, the matrix of the same order. Just as in Karatsuba and Hoffman approach, we can split our matrices in this product into parts. So let's thus assume that the matrix A consists of 4 blocks. And here again, just as in Karatsuba and Hoffman algorithm, we'll assume for simplicity that n is a power of 2. So we'll denote the blocks of the matrix A, A11, A12, A21, A22, just as if this matrix was a 2 by 2 matrix of elements. But these are actually sub-matrices. The same would do for B, and the same for C. Let's try to express the elements standing in the blocks of matrix C through the elements standing in blocks of matrices A and B. So if we take some elements in C, standing here, for instance, this element stands on the intersection of some row of matrix C and some column of matrix C. Now, this element is computed as a scalar product of this row of matrix A and this column of matrix B. And the scalar product is computed by taking elements y by 1 left to right in this row and multiplying these elements 1 by 1 on the elements of this column. And we see that the elements that belong to this part of the row will be multiplied by the elements belonging to this part of the column. So actually elements of the block A11, they interact with elements of the block B11. And this actually allows us to write that C11 is equal to the product of two blocks A11 by B11 plus A12 times B21. So it's checked by the kind of reasoning we just performed. And in the same vein, we can express all the other blocks of matrix C as submatrices as these sums of two products of blocks of A and B. So we see that matrix C Actually, if it were a matrix of size 2 by 2, the elements of C would be computed by exactly the same formulas as we have for blocks of this large matrix C. Now, if we employ this approach to recursively compute these products and then combine them to get the complete matrix C, we obtain that our complexity of multiplying two n by n matrices does not exceed the complexity of 8 multiplications of matrices of size n over 2 plus big O of n squared operations, because this kind of addition of two matrices is done in time quadratic on n, just because matrices have quadratic number of elements. But then the master theorem tells us that T of n is big O of n to the power of log 2 8, which is big O of n cubed, which is not great again, because big O of n cubed is the school book multiplication complexity of matrices when we just use the definition of how to compute elements of C as scalar products. Each scalar product of a row of A times column of B takes linear time, and there are n squared elements in C, so we get cubic time. So again, we are trying to improve on this, putting 7 here, and thus reducing the power of n. But how do we do this? So here we have 8 multiplications. How do we now get 7 of them? By the same idea as for multiplication of numbers, but with great difference, with great, I would say, ingenuity. Because if you look on the formula that was in Karatsuba-Hoffman algorithm, if you kind of make this an exercise in a textbook, this exercise has great chances to be solved. But even if you know what you need to do here, so you need somehow to come up with 7 multiplications, and then out of these 7 multiplications express these 4 blocks, it turns to be much harder thing to do. But Strassen was able to bring up such equations, and these equations look like this. So we need to compute 7 products like this, and these products, just like in Karatsuba-Hoffman, they are products not of original blocks but of linear combinations of these blocks. And then out of these 7 products we can express by these linear equations all 4 blocks of matrix C. So now we have 7 multiplications in our recursive bound, and still we have some constant number of subtractions and additions, and thus we still have this big O of n squared here, which allows us to bring 7 here. Strassen's algorithm is tight in the sense that if you like to improve on this power of n here, you will need not to try to express the blocks of C in smaller than 7 multiplications, but rather you would need to take, say, matrices of larger splits, like 3 by 3 blocks or 4 by 4 blocks in A, B, and C. So you need to tweak both the base of the logarithm and the number of multiplications that we have here. But the current state-of-the-art matrix multiplication algorithms that achieve better bounds, they are using a different kind of machinery.